Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 17, 2025, about 3 days ago. This paper claims a simple swap, using frozen self-supervised DINOv3 features plus a light residual branch instead of a variational autoencoder, delivers faster training and strong few-step sampling, with 5-step FID about 12.26 versus about 69.38 for a comparable VAE system. The paper is titled Latent Diffusion Model Without Variational Autoencoder, and the implications for model training are quite significant. Beyond speed, the approach improves generative quality while preserving discriminative power for downstream classification, segmentation, and depth tasks. Also, the authors shared the official PyTorch code on GitHub. You'll find the SVG autoencoder and latent diffusion transformer implementations, configs for both modules, end-to-end training and sampling scripts, multi-GPU support, environment and requirements files, and example pipelines. It includes data prep with DINOv3, ImageNet paths, and checkpoint-based image generation. Alright, the code details were covered just now, and Figure 1 presents what that buys us in practice. Figure 1 contrasts the pipelines, showing that replacing the variational autoencoder with the SVG feature space simplifies training. The left plot shows training reaching low FID in far fewer epochs. FID means Friche inception distance, a generation quality score where lower is better. The right plot reports that comparable image quality arrives with many fewer sampling steps. So, Figure 2 shows sample images that illustrate the visual quality of the method. The grid demonstrates crisp textures and consistent object semantics, which matters because the latent space is semantically structured and supports stable diffusion training. The samples were generated with classifier-free guidance, a technique that mixes conditional and unconditional predictions to steer content at strength 4. Inference used 25 Euler steps, indicating few-step sampling. The resolution is 256 by 256. So, Figure 3 explains how the SVG autoencoder turns an image into a semantically structured feature and back again. The left block feeds the picture to a frozen DINOv3 encoder and a lightweight residual encoder that captures fine details. In the center, their features are concatenated and aligned in distribution, which preserves semantics while adding texture. On the right, one decoder reconstructs the image, while another serves downstream tasks. So Table 1 reports system-level performance and shows that working in a unified feature space yields strong, few-step generation. With 25 steps, SVG-XL matches or beats diffusion baselines on ImageNet quality. The best guided score reaches about 1.9 grams FID, which signals highly realistic images because lower is better. Training also converges faster, with competitive results after roughly 80 epochs. Reconstruction remains solid with RFID around 0.65, indicating the residual branch preserves detail without sacrificing semantics. 2 takeaways stand out. Replacing the variational autoencoder with frozen DINO features, plus a light residual branch, makes diffusion training much faster and enables high-quality few-step sampling, and the unified feature space keeps strong discriminative power for downstream tasks. The broader implication is a path towards shared, generative, and perception representations, with future gains from feature compression and better guidance. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.